Thank you very much. Thanks for attending, everybody. I hope this is useful and interesting for all of you. So there have always been a lot of development going on with battery-powered devices, handheld devices, in order to get the product to last as long as possible. I'm sure all of us have had mobile phones that have died after a much shorter period than we had hoped for. So we came out with a way of measuring the ability of a battery to provide the current to the device. In terms of designing in with a battery, there are a number of challenges to do this. So we'll look at that. We'll look at some typical applications for batteries in the marketplace, and then what we believe to be the key attributes of a battery test solution, and how they've been implemented in our case. So a number of challenges in designing batteries in. I'll just wait for these people to get seated. Thank you. The testing can be complex, so the equipment that you need may not be very simple, so it might be expensive, and it may be unrepeatable. In order to get a cell to exactly the same state of charge and then run the same test again and again is challenging, because the cell, as you run through the tests, may also degrade. So the first test may not be the same as the 10th test or the 100th test. So in order to have a repeatable platform to run your test from is a necessity. There are battery models available from a lot of manufacturers will provide those, but again, it is just a model. And if you're trying to design a product that works with a particular cell, then to move from manufacturer to manufacturer may also mean you need to implement a different model. So to sell a product into the marketplace, you typically need to tell your consumer how long you expect that's going to last in a typical condition. And using estimates is not always the right way forward. So generic battery models may not always be the best fit to allow you to advise your end users on how they were going to perform. And again, the engineers don't always know how these models were created. I mentioned already, repeatability is often difficult. How do you create exactly the same starting condition? It may well be that you want to test your device with a full charge battery, 100%. Maybe that you want to try running it from 50% to see how long it lasts. How do you make sure that your cell is always at the same state of charge before you run the test? So there's some typical applications. I'm sure most of us are aware of most of these. IoT devices, wearable devices, so things like monitors for diabetic patients, also heart rate monitors, blood pressure monitors. And then more and more in terms of e-mobility, wheelchairs, e-bikes are now quite prolific, scooters, and then you can move all the way up into much higher power classes of devices like forklift trucks and some automated guided vehicles like the things that you see in an automated warehouse. So what are the desirable attributes of a solution for testing batteries? Well, if you're just testing one device at a time, that again can be quite challenging. If you need to test a batch, surely it'd be better if you could test multiple devices simultaneously. So multi-channel operation can certainly help in that way. It may well be that you're not designing for one particular market segment. It may be that you have multiple devices, multiple situations, and you want to test from a few watts up to several kilowatts or even hundreds of kilowatts, and high voltage as well. The control of cutoff conditions is important so that you're taking your device into consideration. You can read all of the others: capacity rating, state of charge. The constant or dynamic level selection is important, and the pulse width control that goes with this. And again, if you're dealing with high voltage, high current batteries, there's a safety aspect to bear in mind as well. It's not uncommon for lithium cells to rupture with quite dramatic, catastrophic results. It may well be that you want to run your test maybe for a few minutes, maybe for some hours, maybe days or even weeks, just to see how the device performs. So you need to be able to capture that, and you want voltage and current and capacity in order to be able to accurately model what's going on with your device. So we can simultaneously digitize voltage and current, so you're then able to measure energy and power from the cell. Dynamic currents for many devices they don't follow the rules of an ideal situation. You can see this is the current waveform of a blood pressure monitor. So we have very low level signals. You can see right on the baseline down here, some very low level things going on that are measurements and monitoring. And then when the device actually transmits the data back to a monitoring hub, then you have quite high currents as it turns into transmit. So you need a huge dynamic range. If something only draws a microamp or two when it's asleep, and then when it transmits, it needs several hundred milliamps. You can't measure that dynamic range with simple instruments. Things like a DMM, when it goes into auto range, it can't switch fast enough to give you this level of detail. You want something that's sampling quite fast. Whereas a digital oscilloscope could be fast enough, but you don't have the dynamic range. So some of the very low current measurements would be down in the noise. So you need something with a large dynamic range and a good sample rate. So there's a couple of features that this solution offers. The first is what we call a profiler. So this allows you to profile how a battery cell operates. You can see in yellow, that's basically an expanded longer term trace of the view we had in the previous slide. So in yellow is the current being drawn, and in blue, that's basically the voltage that the cell will provide to the device. And in the bottom half, you can see how that equates in terms of the voltage against the green trace, which is the internal resistance of the cell. So all of these three features all play against each other: state of charge, available voltage, and the internal resistance. And the nature of the device's current drain on the battery can also have significant impacts. I think the ideal profile for a battery is if you just take a constant current, it will give you the longest possible life before the battery actually reaches the cutoff point and is unable to continue providing energy to your device. With dynamic currents, every time you take a high current pulse, the voltage will drop and then not recover back to its previous state. So your runtime will be curtailed. So in terms of the benefits that this particular thing offers, is you're able to generate a battery model based on an actual device under test, using either static or dynamic current consumption. And again, you can see on the graph here, we've got the internal resistance in orange and the output voltage in blue. Very, very simple, but this can be scaled, as you'll see in later slides. Here's an example of a typical battery profile. So this is created from this solution as a simple spreadsheet. So you have a column showing the state of charge, the open circuit voltage, and the internal resistance. Now, once you have this, you can then use this model to then create, if you like, your own battery emulator, and that's effectively what this is. So you use the battery model, and you can then use this to power your device under test. So you don't have to keep getting your battery to 50% or 75% or 100%, charging up and then discharging it. You can start from any point you like, from 100% down to 0, in pure emulation. You no longer need the battery. And because it's stored in software, it's actually repeatable. So you can use this again and again and again. So again, benefits of this: you can emulate any state of charge. You can set up what the cutoff condition is for the device under test. There's continuous measurement of voltage and current, and you no longer need the cell. So in most cases with the low power, that's not really a problem, but when you go to high power, if a high capacity cell ruptures, it can be quite dramatic to watch. Then the next aspect of this is cycling. So you want to see how long a battery will last before it starts to degrade. How many cycles can I perform? Charge, discharge, charge, discharge. If If you design a product to work with a particular cell size, like a typical 18650 cell, then in order to save costs, you may decide you want to go for a different manufacturer. How's that going to impact the runtime of your device? If you're selling the device with typical life of a year and it only lasts 6 months, then you're going to start getting product returned. So important to know what the worst case scenarios are. So again, for the cycling, how long does it take before the ability of the cell to give you the energy it's storing, or before you're no longer able to take a full charge? So we've looked at quite small cells typically for this kind of start of the presentation, but we do have solutions for high power as well. And again, the same kind of challenges exist. So how do you create a realistic battery model? You need those 3 parameters: state of charge, the internal resistance, and the open circuit voltage. We need to evaluate that capacity under different loading conditions. So is it a fairly static drain of the current, or is it a very dynamic current drain curve? And we need to understand the battery's ability to deliver charge through different temperatures. So again, you can use this model to effectively show this over different temperature ranges. And then we need to discharge and test the battery with realistic current profiles, even if you haven't got the device. Again, that needs to be repeatable. So the solution that we have is an integrated load combined with an arbitrary loading profile. So effectively what we do is we measure the current waveform that comes from being drawn from the battery. We can then invert that and apply that to an arbitrary waveform generator. So then we're basically creating a load which will take current in exactly the same way as the real device. So we're emulating your device. So the power supply with a sync capability allows for the battery discharge with and without loading. We need to be able to deliver fast transients so that we can test in a real world environment. And this arbitrary capability is key for doing this. So to give you a quick idea, this is a solution. Oh, hang on, have I jumped one? I've gone the wrong way. I do apologise. That's what I wanted to show. So there's an example here. This is up on the top left is a regenerative power supply. So typically, if you're doing really high power measurements, then you would dissipate the energy as heat. So you then have to invest in temperature control for the environment of it, which is expensive. The RP7900A is regenerative, so when you start to sink current, basically it puts it back into the grid. So it saves you money, and it also saves on refrigeration costs. And the battery test and emulation software, there's 2 numbers there, BV9210 and BV9211. The 9211 allows you to control 1 mainframe. And the mainframe I showed earlier is able to have up to 4 modules within it. So you can test 4 devices simultaneously. The 9210 allows you to control up to 4 mainframes. So that could be 16 individual devices. And these particular power supplies, you can parallel them very successfully to achieve up to 200 kilowatts. So yeah, it's quite a wide-ranging solution that covers a lot of eventualities. So any questions on anything that we've covered so far? Anyone using this kind of thing? Yeah.
The question in the emulation part, how do you consider the degradation behavior of the battery? Because even, for instance, in a simple charge and discharge can affect. I think it's one of the reasons that in the first slide you mentioned about the problem in the repeatability of the measurement.
Exactly.
So,
yeah.
Yeah. For instance, some of the stress factors have short-term and long-term effect on the battery. Mm-hmm. For instance, if you use the battery in the really high C rate, it will, in the short-term effect, it will increase the temperature of the battery.
Yes.
That can directly affect on the performance of the battery, and also it will have a long-term effect that will, the battery will reach to the unlinearity part of the degradation sooner. So how it can be?
In terms of the emulation, if I just quickly skip back to the emulation aspect. So this basically uses the battery model. So you're using a real battery, and then you capture that current profile of it, if you like. So from a certain state of charge, what's the output voltage, the open circuit voltage, and what's the internal resistance? So you could then use the cycler, you could stress the battery over a number of charge-discharge cycles, and then you could use the profiler again to capture another battery profile. So you have the profile of a brand new battery, you could have the profile of a battery that's been charge-discharge 100, 200 cycles, and one that's done 500 cycles. And you can then use that. So you have your own model. You have a library of models with different ages, different manufacturers, different states of charge. You can have as many models as you see fit to cover the testing that you want to do. But you're right, one particular profile is basically fixed. So you've captured that once. That's a one-off snapshot of the cell capacity. Okay, good question, thank you. Any others?
Maybe I missed it, but how much can you emulate modules and packs and bigger packs as well, or what are the limitations there? What are your boundaries?
Basically, with the high current solution here, the high power, we can go up to nearly 200 kilowatts and 2000 volts. And exactly the same thing applies. So whether it's a huge battery pack, you can acquire a profile from that, and you can then use that to generate the current to power your device, like for an electric forklift truck.
And I would imagine that you would put in a lot more safety into, because for example, if you're developing new BMS,
yes,
you know, I mean, my prototype 1 probably is not sitting in a battery, you know.
Yes,
and that's one of the reasons why you need an emulator, right? So there is inherently a lot of safety features.
Yes, and obviously it's inherently more safe to use something like a self-contained with shut-off control, current limit, rather than a live cell, which, as you say, you can get sort of thermal runaway effects, which, it'd be quite dramatic for something like a 100 kilowatt solution. Thank you, good question. Anything else? Is anyone doing this kind of testing already?
You said the maximum capacity is around 200 kilowatts.
Yes.
But from what I see, this is a stackable system.
Yes.
So why is the limitation 200? Because the systems we use exceed the 200 kilowatt system by a few kilowatts.
To be honest, I mean, there are obviously limitations in terms of the number of mainframes that you can stack. I've no idea why there is the number that there are, but 200 kilowatts is a number that we're speccing. Whether that could be exceeded slightly, I don't know. I could talk to the product specialist and we can advise if you...
Yeah, we already have an appointment, so...
Oh, perfect. Okay, great. Yeah, so the answer will be forthcoming shortly. Thank you. So as I said, is anyone doing this kind of work already? Anyone designing things with small batteries? Are you doing work with batteries or actual devices?
We do some work.
Okay.
But we do have some emulation, but not of this advanced level, but we do have some emulation.
Okay.
Also,
Okay.
that device that we have at the University of Twente, so it is possible to define the configuration of the different cells and how you want to connect the cells. I mean, emulate different cells at the same time.
If you're able, you can basically set up anything you like. If you can create the scenario using real batteries, you can then capture that. That's your profile. You can then emulate that.
Yeah, because this seems new.
Yeah. Okay, good. Thank you. So as my previous colleague said, we are just at the stand behind Keysight and Acal BFI. So please come visit us, and if you want to try any of this out, it's available for evaluation. We can arrange to get some equipment to you, try it out for a couple of weeks. We can come and help you set it up and make some measurements and see if it's useful. But thank you very much for your attention.